I've been pretty fortunate to be part of the data center industry for about 19 years, and I wanted to share a story just to start off with kind of a very seminal moment in my career. I remember sitting in a car about 8 years ago. I was on a family vacation, and I got a call from Senior Vice President at the time, and she said, "We have a tremendous opportunity for you to go lead something new and emerging, and it is going to be the biggest change in the data center industry. It's going to be so dynamic, and we really want you to go do this." And I thought, this sounds like a great opportunity. And that opportunity was to go lead technology for blade servers. And as a side job, just to kind of fill in from all that work I was going to have to do around blade servers, I got to work with some companies like Google and Amazon and Facebook, who were at the time really starting to grow their infrastructure. And I remember at the time, we didn't even know what to call these companies. We called them Internet Portal Data Centers. That was the term that we used. And I also remember about a year later, sitting in a meeting, and we started to talk about this concept called cloud computing, and just feeling my eyes roll back in my head going, oh brother, another buzzword that we were going to go start using. But it's funny to kind of look back to that moment and really think about how the cloud industry really has changed computing, and blade servers, the original motivation for the job, really didn't turn out to be what we thought it was going to be. And what I wanted to be able to do today is share some of the learnings that we've had at Intel over the past 9 years in terms of what hyperscale computing means to the industry, what it means to you. And part of you may be sitting there saying, well, this will be really cool, it'll be interesting to learn how somebody like an Amazon thinks in terms of their infrastructure, but that's not really the hypothesis that I have. Because what I believe is that over the next several years, by 2025, that about 70 to 80% of all of the systems consumed in the data center are going to be consumed by hyperscale. And while you might think that that means that I'm postulating that all of the infrastructure is going to be consolidated to a few mega data centers, my point is anything but. What I want to be able to describe today is how I think that hyperscale technology is going to waterfall, and that you as CIOs or leaders of IT organizations need to understand these principles and adopt these principles, as they're going to become the foundation for your competitiveness over the next decade. So there are 3 things that I want to cover to kind of help make that case. The first is really the fundamental drivers behind hyperscale. Why do I believe that this isn't just something for the mega data centers or the cloud companies of the world, but really something that really will affect every IT organization? And then I want to talk about what are the best practices. So if you do believe, like I do, that you will be adopting hyperscale practices in one form or another, what should you be thinking about? And then the third piece of it is really about new technologies. How are these new technologies going to fundamentally change the way you deploy infrastructure? What are the things to kind of keep on your radar screen and have people looking at as they start to think ahead about what the inflection is going to look like? So let me start with what really is driving hyperscale. And there are 2 key dynamics. The first is that the fundamentals of the economy and the fundamental drivers of the services that you need to deliver are changing. That IT used to be a service that was to support the business. It's increasingly becoming a key part of the business. If you are in factory automation, if you are in financial services, you know that your ability to deliver that service creates a different customer experience, and that the way in which we interact with devices is continuously changing. The fact that it used to be a PC, and now in many cases it's a phone, and in some cases we're moving to more embedded types of devices, like for example an Amazon Echo. All of those become new places to go deliver services, to go reach a customer. And in many cases it's not about the consumer either. It may be about machine to machine. It may be about analytics behind factory automation, or to do preventative maintenance or repair. But all of those things are attaching all the devices out there delivering new services, and that really is driving the build out of the cloud. So that's one of those dynamic factors that indicate the services themselves are driving the change. The other really is the fundamental economics of computing. And there's this idea called Jevons paradox. What Jevons paradox really is that the elasticity of certain types of things, as the economics improve, the elasticity explodes. And Jevons paradox actually came out of the coal industry and the idea that as coal prices reduced, the actual demand for overall coal expanded dramatically because you actually found better economics at scale. The same thing holds true in computing. And really, the driver of Jevons paradox in computing is Moore's law. And those of you familiar with Moore's law know that it's the density of transistors doubles every 18 months. And if you look back in the 1960s, the cost of a transistor was about $150. Today, for a penny, you can buy 70,000 transistors on a chip. So the economics are dramatically different. And in fact, if you were to apply that same level of economics to a 1971 Volkswagen Beetle, you'd find a car that can drive 300,000 miles per hour, that gets 2 million miles to the gallon, and costs about $4. So you can see that those sorts of economics are not something that's readily produced in many industries, but yet that's what's been driving compute. And what you see on this chart is that it's been the driver behind the move and the shifts of compute. It used to be that the cost of computing was so exorbitant that only few could afford mainframes, and we had an industry that time-shared them. And then we actually could create personal computers, and we moved to client-server computing. And then we moved to phones because you could drive enough compute power into a handheld device. And we moved to mobility and mobile computing. And now we're reaching yet another phase with the Internet of Things, where there's enough computing power that can be built into wearables, that can be built into embedded home devices, that can be built into factory automation and machinery. And so it's all of those devices that are really now going to go drive a tremendous amount of compute. You can see the chart that shows that we're seeing a tremendous increase in the growth of internet traffic, which would be natural given the number of devices that are being connected together. So these fundamental advances in Moore's law are changing the way we do compute. And this too is going to and is continuing to change the way cloud computing is deployed. And this is my fundamental argument for why cloud computing is something that will be fundamental to the masses, and hyperscale technology is something that's critical to understand and to be able to adopt beyond just public cloud service providers. It used to be that, again, the economics of cloud computing, the ability and the expertise required to stitch massive numbers of systems together, make it scalable, make it resilient to go deliver a service, was really limited to the few. And cloud computing was about what I would call a phone book, putting together a web page, a Yahoo-type portal, if you will. And then it eventually evolved into intelligent search-type services. And then that same level of scale allowed companies to innovate in terms of e-commerce and social media. And so you can see those economics and the level of expertise as it broadens, and as the economics improve, more can be done and more uses come online. Now today, when you look at cloud computing, about 2/3 of the actual usage is in consumer-based applications. That's going to change dramatically over the next decade, especially as we see the growth of the Internet of Things. We're going to see new industrial applications, analytics, machine learning, visualization, autonomous driving, personalized medicine, a converged view on risk analytics. All of those types of mega-scale applications, the types of applications that you in the audience are going to be deploying over the next several years. Things like natural language processing. These are real applications that will permeate just about every business. They're going to require cloud computing as a fundamental service enabler, and they're going to require hyperscale computing practices to be able to deliver those services efficiently. So if we say that we accept the hypothesis that it's going to be something that's going to affect just about everyone here, what are some of the best practices? What can we learn from what some of the largest cloud service providers are doing in hyperscale computing? Well, one of the first things that they do is really design for agility. And I think one of the best examples is software-defined networking. If you look at what it takes today to go deploy and physically provision a network, there are multiple steps. You have to get the hardware on site, you have to go get it installed, you have to bring it up, you have to go provision the network, then you have to load applications. It's probably optimistic that in many cases you can do that in weeks, because in really to do the planning, you actually have to do that well in advance. The idea is that you want to be able to take those new services that your customer base, your internal or external customer base, wants to deploy, and to be able to do that in a very rapid manner. And that's where, again, software-defined networking comes in, and you can see how companies that have these best practices, that have a cloud infrastructure, that are deploying at a hyperscale, can take that time to go provision a network from weeks down to a matter of minutes or an hour to be able to go provide those services. It's that type of agility that's not just about IT infrastructure, it's about being competitive as a business. The second piece from a best practices perspective relates to the economics of cloud computing. And this is, I think, a really relatively seemingly simple but a very important principle, is that you need to be able to measure the effectiveness of the service that you're delivering. And what we've seen is that the best companies that deliver services know what their performance metric is. So they're looking at their workload. It could be how many virtual machines that are being delivered. It could be how many queries per second. It could be the number of web responses. Whatever it is that you're trying to deliver in terms of a service, that's the numerator of this equation. And then the denominator is the cost to go deliver that service. Now, I really hope, those of you that know James Hamilton at Amazon, I hope he updates this, because it looks like my chart might be a bit out of date. But we've found for the most part that this pie chart tends to hold true, and that the leaders that are deploying cloud services, about half of the cost to deliver that service comes from the cost of the systems, and about another quarter of it is proportional to the power delivery. And then the other quarter is sort of split between a whole bunch of things, including software and the people required to go make that happen. And this is a really fundamental principle, because it will guide how you deploy applications and how you deploy and where you deploy your overarching infrastructure. And as I talk through the technologies in a little bit, you'll see how they apply to this equation. I do want to relate kind of another story that helps to apply this. You know, a few years ago, I remember getting this really urgent call from some of our field salespeople saying, we need to go drive low power. Low power is where it's at. We need to have lower power processors across our product line to be competitive. That's what the customers want. And we added a whole bunch of these lower power processors. Well, guess what? Lower power processors also have lower performance. It's just a fundamental trade-off that you have to make of physics. Well, if you look at this equation and you say, if I can cut the cost of power by 10%, and I can cut the cost of performance, or my performance goes down by 10%, I'm actually going in the wrong direction. And that's exactly, in fact, what happened, was that customers looked at it and said, wait a second, I have to give up performance. I don't want to give up performance, because performance is more important in this equation. Therefore, I actually want higher performing CPUs. And one of the interesting things that this led to over the next several years is that more and more of the leaders in hyperscale computing are actually using the fastest, higher performing systems. So sometimes people hear that a company like a Google or a Facebook uses low-end, commodity type hardware. They certainly want it to be, as cost effective as possible, back to this equation, but they're not willing to compromise on performance, because it affects the overall cost efficiency of delivering the service. So this is one of the fundamental approaches in driving the best practices. Now, you may be looking at that pie chart and saying, there is no way that my IT infrastructure looks like that. I have a giant piece of the pie that's dedicated to personnel and people and overhead. And that's actually to be expected. One of the things that we did is we put together an analysis to look at what we see as current practices in the IT industry and what it really costs to deploy services. So we did an analysis here. It was 10,000 operating systems instances. within the infrastructure and what it costs to deliver them over a 5-year time horizon. And you can see that people is a big portion of it, but so is software licenses a big component of it as well. And when you actually look at applying some of the best practices back to hyperscale, looking at things such as how to go use intelligent workload placement and orchestration, how to automate the provisioning of new services or new virtual machines, having things like a self-service portal, all of those reduce some of the needs for the IT overhead to deliver that service. There's also a key element of optimization. Still today, in many instances, the IT infrastructure itself is underutilized. And how can we find ways to do a better job of workload placement and workload optimization to make the most of that capital investment with the infrastructure? Again, hyperscale best practices really do apply in helping to reduce that cost. And then, of course, there's a tremendous amount of leverage around standards-based business practices, whether it's standard servers or open source software, ways to be able to help reduce the cost, but also increase the flexibility of the infrastructure as well. And so these types of things we found can go cut about 50% of the cost of service delivery to making a hyperscale or making a cloud infrastructure more effective. Another area that I get questions a lot is, hey, Jason, when I look along the horizon of optimization, where should I be? And there's really no one answer. What we found is that depending upon the size of the infrastructure, it'll sort of dictate the strategy for optimization of the infrastructure as a whole. So if you look at a company that may have hundreds of servers, what I would typically recommend to them is to say, just by making sure you're using standards-based hardware, you're trying not to use too many things that are proprietary in general, you're probably doing a pretty good job using standard servers across the broad portfolio of hardware from OEMs. Not trying to specialize too much, and obviously virtualization is a huge improvement in terms of the efficiency and the utilization of that hardware. As you start to get to thousands of servers within the infrastructure, what we find is that automation, that software-defined infrastructure, becomes increasingly important to driving the overall efficiency and optimization. And this is also where we start to see companies look for a more improved efficiency in their hardware. I'll talk a little bit about open compute in a bit, but one of the benefits of open compute is taking some of the best practices in hardware design that were developed by companies like Facebook or Microsoft or Rackspace in the industry and really enabling it to be more accessible to the masses. And so there's a case where as you start to look at that type of infrastructure, an open compute type of approach starts to become interesting. Now, as companies reach tens of thousands of servers within their infrastructure, what we start to see is they tend to own their own data centers. They'll optimize from the data center all the way down to the equipment. They'll look at their actual workloads and start to profile them and say, this type of software will run best on this type of system or hardware. They may specify the components and get more prescriptive on the sizing of those actual systems themselves. And telemetry starts to become increasingly important. How do I know how my systems are behaving? Because I have to manage it at scale. If you're at tens of thousands of servers and you don't have that insight into the overall infrastructure on a scalable manner, it really starts to become unmanageable. Now, as you get to 50,000 servers, 100,000 servers, the level of optimization tends to increase. And this is where we'll start to see companies that will design their own servers or systems. Again, Facebook taking the open compute approach. They were very clear. Google has been public about the fact that they've designed their own servers as well. And we're starting to see that increasingly deployed as an approach across the industry for companies at that scale. And even in some cases, because a workload may become so impactful and so important. So if I think about something like visual computing or image recognition, in some cases, the scale may be such that they're actually starting to design their own intellectual property, their own silicon, and wanting to take those IPs and collaborate with us to deliver something that's a highly optimized system. So the level of optimization and customization really is impacted by the overall scale of the infrastructure. Now, you shouldn't view that spectrum as static. The reality is many companies, as they grow their infrastructure, will go through some sort of life cycle. And I wanted to share one example, which was Dropbox. Back in 2007, they were looking at a hybrid type of approach where basically all of the block storage itself was being done at Amazon, but the metadata, the web servers were done within their own data centers itself in kind of a hybrid storage type of approach. Now, over time, as they started to grow that infrastructure, as it went from 40 petabytes to upwards or close to 500 petabytes of data that they were storing within their infrastructure, they started to realize that they needed a more specialized approach, that given the scale that they had, if they designed their own server that was highly optimized for storage workloads, they could do a couple of things better. They could drive better economics overall because they were highly optimizing for what they were doing. And then they also could manage that service, kind of take control over what they were doing, how they were updating it, how they were managing it, and really driving the customer experience into their own hands through their own infrastructure and their data center. So starting in 2013, they built their own software stack, they built and designed their own hardware, then mirrored it between 2 locations in 2014, and then brought 90% of their storage in-house. So you can see how this life cycle occurs, and sometimes they tend to ebb and flow. But you start off using cloud services as you're rapidly building scale. As you start to reach some sort of steady state and need for optimization, you'll see companies tend to take more matters into their own hands and then evolve that infrastructure going forward. So there is a life cycle to this. Now, all of this sounds great. I mean, understand the economics, understand the value potentially of it, but how is it implemented? Because at the end of the day, if the bar for expertise is too high, the economics don't really matter. It's too difficult to be able to do. And this is where I think open source is having a tremendous impact in bringing hyperscale technologies down to the masses. Now, many of you are familiar with OpenStack, and I just use a couple of these as particular examples, although I'll get to a more comprehensive list in a little bit. But OpenStack obviously is bringing some of the software components that you would want to have in a scalable, highly automated a cloud stack together as an open source project, and allowing companies, instead of completely building their own from the bottom up, to have a reasonable start. And we're starting to reach the point, I think now, it's taken a long time for OpenStack to reach the level of enterprise maturity that's really required to kind of get more deployment. And so the level of POCs that we're seeing is really starting to grow exponentially. Now, we tend to think about open source very much in the software domain, but really that's what open compute has really shifted the focus toward hardware as well. And so the benefit of the Open Compute project was taking some of the designs that essentially have been open sourced from Facebook, from Microsoft, and from other companies, and allowing them to become available to the masses. Not just that you can adapt or purchase one of those systems that previously might have been thought as proprietary intellectual property, but also that you can see those reference designs and you can actually improve upon, build upon, and adapt. It truly is open source hardware. And for those of you that aren't familiar with it, it's beyond just the server system box. It also is highly specialized designs for storage, mezzanine cards for I/O, rack designs. Google even contributed a power distribution unit design. So there's all kinds of hardware-based infrastructure that's now being put into the open source domain. The other thing that we see open source doing is aligning industry around standards. Now, Google, for a while, has been a leader in adoption of the use of containers within their own infrastructure. But even now, they too see the value of working broadly with the community. And the Cloud Native Computing Foundation has been one of their vehicles for taking the Google infrastructure, their orchestration, their use of containers, and really helping to build a community around that. So what we're seeing now is that the bar and the barrier that used to exist, not just the economics, but also the complexity, both coming down substantially and really becoming an enabler to allow more companies to build their own hyperscale infrastructure. So now, what are some of those things if you were to start moving down the path of hyperscale infrastructure and taking on those best practices. There are a number of technologies that I think over the next several years are going to be game changers and things to think about as you build out that infrastructure. The first goes to compute and workload optimization. Conventional theory a number of years ago used to be that you wanted one type of system within your cloud, and there was a lot of good reasons for that. It came down to flexibility. If I have one system and it's repeatable, it seems scalable, and if I move workloads around, it doesn't really matter at the end of the day because I've got those consistent building blocks across the cloud. But now what we're starting to see is that because a number of these workloads have specialized requirements, that there's a higher degree and a need for customization and optimization. And so really thinking through back to that total cost of ownership, that approach to looking at the cost of delivery of a service, optimizing the workload for different types of compute is going to be critical. And so part of Intel's strategy here is to be able to allow a spectrum of different types of compute. And in many cases, we still think general purpose types of infrastructure based on things like our Xeon processor, which predominantly powers most of the servers today, will still continue to be the main processing going forward. But then you look at high-performance computing, things like supercomputing applications, those of you that might be doing risk modeling, or you might be looking at applications for computer-aided engineering. Those require highly parallel processing, and something like a Xeon Phi may be more optimal to delivering that cost of compute. We also recognize that there are certain algorithms that are being built. So for example, high-frequency traders build their own algorithms, may want to accelerate them, and FPGA may be more applicable there, or in some cases even a highly optimized ASIC. So there really is truly a spectrum for the level of compute required, and I think having the understanding and really looking at the full spectrum of what these things mean is important to the overall efficiency of the compute being delivered. The second thing that I think is going to really be a game changer is that there's going to be a new tier in the memory hierarchy, and this also will not just fundamentally change the economics, but it'll change the way that companies write software and how they deploy applications. What we are going to be delivering over the next couple of years is a new technology called 3D XPoint. Now, today, most systems have DRAM, and then they have some sort of storage or I/O. And even when you look at the difference in latency between DRAM and NAND, you're talking about tens of thousands of order of magnitude in terms of latency and performance. So it's very clear today why we have the application hierarchy that we do about what goes into memory and then what we decide to go ahead and store and write to disk. But when we insert something in that's a new memory technology, and this new memory technology will essentially have nearly the performance of DRAM, it will have a much dramatic cost advantage versus DRAM, say about half of the cost of DRAM. That really allows you to have a much bigger memory footprint per server. And on top of it, it also allows you to potentially do applications or do certain things that you would normally write to disk in memory itself, enabling classes of in-memory analytics or other types of applications that weren't done previously. The other thing that has a benefit to it is because this is non-volatile memory, you're able to go ahead and store things and persist things in memory that you weren't able to go ahead and do before. So bringing together the memory and the storage hierarchy together will fundamentally change the way that systems are architected, but they also will fundamentally change the way that the rack itself is architected as well. We believe that the building blocks of compute for hyperscale will be done at the rack level. Most of the infrastructure that will be deployed to deliver big applications, to do high-performance analytics, and to deliver services at scale are going to need a more efficient building block. And I remember a number of years ago sitting actually in our cafeteria talking to one of our smartest architects. And I just remember asking the question, why is it that we know that cloud and software-defined infrastructure really wants to create pools of compute, network, and storage? but yet we're still providing these really incremental building blocks of compute, network, and storage. We sell these pizza boxes of 2U servers. Why aren't we thinking differently and really taking a fresh, clean sheet approach to the way hardware is deployed for hyperscale computing? And that really led us to go create the rack scale architecture. And I think this is going to be another fundamental inflection and a game changer in how hyperscale computing is delivered. The idea is not thinking so much that it is the rack itself, but maybe several racks, but the ability to take a higher level of systems that can be delivering pooled compute, pooled network, and pooled storage, and to allow for much more automated provisioning through APIs that expose the dozens, if not hundreds of systems that are pooled together. That's really what we want to be able to go deliver. And that's the fundamental idea behind rack scale architecture. And so this is something that we're working across the industry with both hardware vendors as well as software vendors, for example, like VMware, to make sure that there is this efficient way to go take a cloud operating system and infrastructure and deploy it across these pooled hardware. The benefits that'll come from it are that we'll see more efficient utilization of that infrastructure, which again affects the overall effectiveness of how you deliver a service. It'll improve the lifecycle management. One of the things we also look at rack scale architecture and ask is, why is it that every system that gets deployed still has to have a PCB, still has to have sheet metal, still has to have fans? How can we find a way to allow users, IT such as yourselves, to be able to upgrade and purchase the components that are required that are delivering more value to your application? So we're going to be improving lifecycle management over the horizon. And then also improve the data center operations, finding ways to make it easier to manage these systems at scale through these APIs, and making sure that they're validated with the leading cloud software stacks across VMware, Microsoft, Red Hat, across the entire industry. So doing this right will mean, again, that the barrier to efficient hyperscale computing is lowered and more adoption across the industry. Software-defined infrastructure, though, is going to be required to go manage all of this innovation. And we're spending a lot of time at Intel enabling the industry. The left-hand side of this chart really is a simplified diagram to kind of highlight how we think about it. We think about there's going to be a virtualization layer. It could be VMs or it could be containers, that we need to have an intelligent orchestration layer to be able to do workload provisioning and do it efficiently and automate it, and at the same time make sure that all of this is scalable. And to enable this to happen, I wanted to share some of our favorite projects out there in the open source community. Some of these you're probably very familiar with, and others maybe not so much. Things like Habitat and Ansible for application deployment and helping to package and deploy that infrastructure, sort of the DevOps layer of projects. Thinking about how we do more intelligent workload optimization. And there's a number of scheduler and workload provisioning projects that are of interest. Kubernetes is one that's coming out of a Google-led effort as an open source project based off of their own infrastructure that highlights the scheduler. Mesos, which is a project that's been around for a while, has been focused on database messaging and SaaS types of applications. OpenStack has its own scheduling work and obviously provides an entire or a relatively complete stack for cloud automation. And then you've got Calico, which is a highly scalable, pure layer 3 approach to networking. So a number of open source projects that really can help with deploying of the infrastructure. And then at the lower layer, there are a number of projects that I think are of interest. The turtle represents a project that we at Intel initiated called Snap. And what Snap is about it's about intelligent telemetry and exposing all of the hardware metrics from the platform. You probably are familiar with Docker and CoreOS, kind of at the infrastructure and the container layer and what they do. etcd from a scalable key value store database. Things like Ceph for storage. So all of these components together are becoming robust. We at Intel are investing in all of these projects, and I think they're great resources for you as you start to think about the software-defined infrastructure and architecting that out for the next decade. So I want to summarize with 3 key elements that we talked about. One is that I do think that cloud and hyperscale is critical as an enabler for services. It started with the elite, it started with the largest data centers, but as the economics improve, both due to Moore's law as well as the barrier due to open source, those fundamental enablers will allow you to go deploy hyperscale infrastructure, and it will become a fundamental competitive advantage to you as a company and how you deliver that infrastructure. The optimization and the competitiveness of that infrastructure is defined by 2 things. It's the size and the scale of that workload, and actually the workload itself, what it needs to do. Is it a high-performance computing application? Is it a cold storage type of application? Those 2 will drive the overall efficiency delivered by that total cost of ownership model. And the last is that I hope you find some of those technologies that we're bringing to market interesting. I think that they will become building blocks to allow you to be competitive. They'll be game-changing in terms of the application. And we at Intel are looking forward to working with you to help make sure that your applications and your infrastructure is scalable, efficient, and successful.